Those were some of my best 3 years. That's when I met Tregeozunim and we started working together. And, you know, ever since I left Korea, it's always been a privilege and an honor to come back to Korea like once a year to work with Professor Tre. And, you know, unfortunately, this has been very difficult for the past 2 years for reasons you all know. But I'm very happy that at least today I can give a talk that hopefully will be of benefit to many people. So let me start by sharing my screen. I don't know if I'm oh, perfect. Yes. So that's going to start now. Wonderful. All right. So my talk today is about irrationality in algebraic geometry. Yeah, so I have one goal, which is to understand this image here. So if you just look at this image, so we see we have two persons who are trying to very, very hard to do something. And we have 숙명여대 수학과 눈송이, who knows that it's impossible. Yeah, so she knows because she did the math. So she knows whatever these guys are trying to do, it's impossible. So my goal today is that by the end of today, you understand in this picture why they are doing a fool's game, why what they are trying to do is impossible. So hopefully by the end of today, we are all Nunsongi. And this image was done with help from my brother, Philip van Garrel. So thank you, little brother. All right, maybe take a few moments to think about what is happening here. Yeah, just think a little bit about it. You don't have to tell me, but just think about what is happening here. And then later during my talk, when we come back to this image, you can compare what you were thinking, what you're thinking now with what you will be thinking later. Okay. And before I start to get into the mathematics of my talk, I want to do a little bit of an introduction, since I think we all, I mean, all of you have studied mathematics for a while. And so let's just talk about, maybe some of you are thinking about doing a master in mathematics, perhaps even a PhD. Maybe you're thinking about becoming researchers in mathematics. So now let me ask you a question, which is, what do you imagine the life as a researcher in mathematics is like? In other words, you know, Professor Tre is a researcher in mathematics. I am a researcher in mathematics. What do we think we do on our day-to-day basis? Yeah, just take a couple moments of thinking about this. You know, when we're not giving talks about irrationality of mathematics, what are we doing? So when I was young, I really had no idea what research in mathematics is like. And if you had asked me that question at the time, maybe that would have been my answer, namely a really, really long computation. So this is, I think you can recognize this number. Also, Nunsongi knows what this number is. So when I was young, I imagined maybe it was very difficult for me to imagine what it would be like to do research in mathematics. And maybe I thought it would be something like computing very, 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 very big and long numbers. So one part of my goal today is to give you a little bit more of an idea of, you know, give you an idea of the day-to-day of research. In fact, when I would visit Professor Chue, when I would come to 숙명여대, I would visit him every day. We would go to his office, maybe have some coffee, and it would always be really interesting to discuss mathematics. There would be a back and forth of ideas, of computations, of understanding. So I have very good memories of this. All right, so what is mathematics to you? And that's my next question. Like, what do you think, what does mathematics feels like for you, you know? Like, is it a, yeah, whatever, what is it? You know, when your friends ask you, what is mathematics? What do you tell them? So, you know, mathematics has many, many aspects, and this is one of them. So here, this was in summer of 2016. So this is in Paris, and so we were at a conference in Paris. I think it was Collège de France. So I took the image, and you can see Professor Chue and some other mathematicians. So something that mathematics has to do is you make friends all over the world. And then sometimes you travel to exciting conferences where you meet people from all over the world. So I think that's really a very enriching part of mathematics, that you're able to, you know, make friends with people from different places, from all over the world, that you're able to travel to conferences and talk to other mathematicians, learn new things. So very, very good memories here. Of course, it's been a bit harder to travel for the past 2 years, but probably it will come back in some form or another. All right. Now comes the moment where I give you some advice. And I thought about, in preparation of this talk, I thought about what is the best advice I ever received in relationship to mathematics. And I think the best advice I ever received was by my mentor during my MSc studies in Lausanne at the Swiss Federal Institute of Technology, EPFL. And so Professor Eva Bayer-Flukiger. And basically she said, so I was doing my master, and she told me, go to the USA for your PhD. So I wrote it a little bit differently, because it doesn't have to be the USA. It could be, I don't know, Germany, it could be France, it could be England, or it could be lots of different countries, maybe China, you know, who knows. But I think it's very, I mean, of course, it could be going to Korea if you're European, like me. And I think it is really a very good thing for your mathematical thinking, for your creativity, to go to another place, to interact with people who think about mathematics very differently. So personally, when I learned, well, high school was in German, so I learned mathematics the German way. Then university was in French, so I learned university mathematics the French way. I went for my PhD to the US, and then I learned the American way, and all of them are very different. And when I came to Korea, it was again like a different type of thinking about mathematics, and it's really useful to have all these different perspectives. All right, and you know what I'm saying here, I'm not just inventing it. It's actually, I mean, there are research articles in actually economics and psychology, so economics and psychology, that study that phenomenon. And one of them, this article here, they studied they studied papers in economics, and they found out that if the names were from different cultures, like, you know, maybe Korean name and Swiss name, who knows, then usually the quality of the paper was higher. It would be published in better journals. It would have more citations. Really interesting. And the other one is about, I think it was an MBA program in the US, and they found out that the more the international students interacted with the local students and the local population, the more they were creative, innovative and the better entrepreneurs they become when they went back home. And in fact, I just want to add something else, which is, a lot of fairy tales. So, here we're talking about this idea, go abroad, right? And a lot of fairy tales are about this, Hansel and Gretel, they're like lost in the forest, something terrible happens, and then they become, stronger. And also there's this hero's journey, which is a lot like that. Like Odyssey, he has a very, very long journey, many crazy things happen, and then he comes home and he's stronger. I don't know about the Korean analogs, but I'm sure there are plenty. All right, so that's my, I guess, non-mathematical introduction. And thank you for bearing with me. And now let's start to do some mathematics. My talk today is about algebraic geometry. This is the domain of research of both Professor Trey and myself. And algebraic geometry is, roughly speaking, the study of geometric shapes given by algebraic equations. So you start with an algebraic equation, or in fact, you could have several algebraic equations, and then they trace out some geometric shape. Here I use Mathematica, which I use the department license of Mathematica, and I drew this shape. So you get this extreme, to me, very beautiful shape. You can see there's like some holes. You can go in here, come out here. With Mathematica, it's really fun. You can turn it around, you can look at it, etc. And yeah, so that's an example. And when you have a class in a new topic, the first question you always ask yourself is, what are the simplest shapes? So of course here so the simplest possible shape is of course the point, the point. So we all agree that's the simplest geometric shape. But then the second simplest would be the line. So for a line, you have one direction, like one independent coordinate. Then the next simplest one would be the plane. So here we have two independent coordinates. Yeah, everywhere you go, you can just go in this direction for as long as you want, or you can go in this direction for as long as you want. And if you move in this direction, the other direction is not affected. And so we're going to call for today, we're going to call these n spaces. Yeah. So you might want to, one way you could just think about them is just a1 to the n, if you know what that means, or c to the n, or you could think about this as r to the n, whichever you prefer, or q to the n if you prefer. So it's just these n spaces. We have the simplest type of object, independent directions, dimension n. And then they have coordinates, which is like, I'm going to call the coordinate for the line, I'm going to call it t. In the plane, it will be x, y, and then x, y, z, etc. Or, we can have x1, x2, x3, blah, 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 xz, something like this. All right. The simplest possible geometric shapes. And so here are some scary equations to wake you up, to make you feel scared of what's going to come next. But that's just, what I'm trying to do here is that sometimes you see an equation like this that is could be quite scary. But you should always remember that for each equation corresponds to a shape. Yeah. So even though these equations might look a little bit terrifying, in fact, they correspond to a beautiful shape. So for example, if we take x squared plus y squared equals 1, that's a circle. A circle is not a scary object. That's a circle here. Yeah. And that's a very, very strong feature of algebraic geometry, is we always go from equation to shape, from shape to equation. There's always a back and forth. So there's a back and forth. So we always should keep in mind the shapes. They give us some geometric intuition, some understanding. But then sometimes we need to think about the equation because we're working with the equation. Yeah? Always this sort of back and forth between the two. Sometimes it's convenient to work with equations. Sometimes it's convenient to think about shapes. And then, and so the first type of question one can ask is what is, let me put it here. What is the fundamental shape what is somehow the simplest possible shape? And we saw that somehow the simplest possible shapes are like line, plane, etc. Yeah, so I guess the answer to this is, so if that's the question, the answer is n space. Yeah. But maybe now let's ask the next question, which is which other spaces or shapes, I'm going to call them shapes, which other shapes are essentially like n spaces? So it's like, which other shapes should we also consider to be like n spaces? And this may seem like quite a simple question, and it is a simple question, but it is extremely hard to answer. So this is extremely hard to answer. And this is something I'm talking about today. So let's look at two shapes. So we have this line, that's our one space. That's our one space. And let's look at the circle. That's the thing we defined before. And now, are they, so the question we mentioned here is, we ask which other shapes are essentially like n spaces. So here, are they essentially the same? And when I say this is, how do I want to answer this? Well, I want to answer this from their equations, And the question I'm asking is, can we transform one equation into the other? And if we can, then we will say they are essentially the same. Of course, you know stereographic projection, etc., etc. So somehow in some geometric way, we're kind of trying to wrap this around here. Yeah. But I don't want to go into this analogy too much, because I'm asking, we have two shapes, are they essentially the same? And the way I want to say they're the same is by transforming their equations from one to the other. So let's do it. Let's do it together. So here we have the line. It has coordinate t. And here we have this the square, sorry, the circle. It has coordinate x, y, for x squared plus y squared equals 1. All right. And now how can we transform one into the other? Well, I'm going to make a wild guess, which is I'm going to send t to t squared minus 1, t squared plus 1, 2t divided by t squared plus 1. If you ask me why, it's just, I just dreamt about it. And then I'm gonna, so that's one way, it's morning here, so I'm still in my dreams. And now And we're going to go the other way as well. That was my second dream, which is we're going to take x, y, and we're going to send it to x plus 1 divided by y. Yeah, so we're kind of making a map between the two equations. Okay. So now, because you have had a very good mathematical equation, you're of course immediately asking, is this legal? Is this legal? Yeah. And that's a very good question. Thank you for asking. So meaning legal in the sense that, does it satisfy this equation? Yeah. Does it satisfy this? Does it satisfy this equation? Well, let's check it. Let's check it. So let's check it. So we have to check that t squared minus 1 divided by t squared plus 1. So that's our x coordinate. If we take it, I'm going to write it like this. If we take it to the square, and if we add the other coordinate to the square, 2t divided by t squared plus 1. So if this was a legal move, then this equation has to be satisfied, namely x squared plus y squared has to be 1. So this is x, we take it to the square. This is y, we take it to the square and we sum it up. And now there's no way in the world this can possibly be equal to 1, but let's check it anyways. So at the bottom, we have t squared plus 1 to the square. At the top, we have t squared minus 1 squared plus 2t squared. This is equal to, so you probably already solved this, but I'm just going to do it in my very slowly. So this is t to the 4 minus 2t squared plus 1 plus 4t squared divided by this one I'm going to leave because it's too hard. And then we obtain, you can see that this is just t to the 4 plus 2t squared plus 1 divided by the same at the bottom. And now the top, we can simplify to t squared plus 1 squared divided by t squared plus 1 squared, and miraculously we get 1. So it was a legal move all along, fortunately. So my dream was a correct mathematical dream. Okay, and then the other way around. Well, the other way around is a legal move because this just has to be an element in our on the line, and it is an element on the line. Yeah. Of course, you might wonder about what if y equals 0, but we're talking about equations. Yeah, we're talking about like variables. So a variable is not equal to 0. It's just a variable. Okay. So let me give you a little summary. So we have a line which is parameterized by a coordinate t. We have a circle, which is the x and y subject to this equation. And then we transform one equation or one coordinate into the other and back, yeah? So that's, and now I'm going to define a mathematical concept, very, very specific mathematical concept. It's called a magic trick. And so magic trick is going to be when I start with one coordinate here, I transform it to the other coordinate here, and I go back and I get back to the same. Okay. That's the first condition. The second condition is I start with on the other side with the coordinates on the other side. I go over and I come back, and again, I got the same. Okay? So the magic trick states that if we start with an N shape, and we N space, and we go over to some shape by a transformation and back, then if this and this is the idea, and so if, maybe I should, let me try to use, if, so this is going this way and this is going this way. If this composed with this is, maybe I shouldn't write it like this, this and this is identity, and going back and going forward 2, then now I'm running out of space, then I'm going to use the advantages of having a tablet. So we have an in shape, n space, and we have some transformation from one to the other. And then we say that if doing one transformation and then the other is the identity, and doing the other and the first is as well, then shape is rational. Yeah. So in other words, we defined by magic trick what it means to be essentially like n space. Okay. And what I want you to take home is we're making a transformation to equations, and if the transformations get us back to what we started with, then we are essentially like n space. So this is a condition about the equations. Remember, we always have either the equations or the shape, and here we're working with the equations. But you know, this may seem a little bit funny. Let's just do it in examples. Yeah. So in the example we had before, so this is going from the line to the circle, and then back to the line. Yeah. Remember, those were our equations. So we start with the line, we go to the circle, and then we go back. So we take x, y, and send it to x plus 1 divided by y. So this is x. So we send it to x plus 1, and this is y divided by y. Yeah. So x plus 1 divided by y. Okay. And now the condition is we should be coming back to the same we started with. That's of course completely impossible, but let's check it nonetheless. So let's check this. So this is, so we have t squared minus 1 divided by t squared plus 1, and then plus t squared plus 1. Yeah. So I made this into t squared plus 1 divided by t squared plus 1, and everything divided by 2t squared plus 1. Now, we know we can simplify this. We know these cancel away. So we get 2t squared divided by 2t, which is miraculously equal to t. Yeah. So starting from t, doing this transformation, and then doing the other transformation, miraculously, we got back to t. Okay. What about the other direction? So here we start with x, y. We send it to x plus 1 divided by y. And then we do this funny one, which is, right, it's t squared minus 1 divided by t squared plus 1 to t squared plus 1. So this is, so this is t. We send it to t squared minus 1 divided by t squared plus 1. That's the x coordinate. And then the y coordinate is 2 times t. So that's 2 times t divided by t squared plus 1. Yeah. So that one's a little harder. So let's first understand what is this one. So x plus 1 square. So we're just playing around with equations. So this is, so we're gonna just multiply it. Actually, I'm gonna take the, I think I'm gonna, yeah. So this is x squared plus 2x plus 1 divided by y squared, but then I'm going to take the 1, I'm going to make it a y squared over y squared. So this is minus y squared. So how is that possibly useful? Well, we know that x squared plus y squared is 1, which means that 1 minus y squared is x squared. Yeah. So that 1 minus y squared is actually an x squared. So the whole thing equals 2x squared plus 2x divided by y squared. All right. So we use the fact that we know that this relationship is satisfied to simplify this into this expression. Okay. Now let's do it for the bottom one. So it's almost the same, but plus y. So again, we keep the y square at the bottom, and the top we simplify, we compute out like before, but now instead of minus y squared, we have plus y squared. And again, we're going to use this equation because we have x squared plus y squared, and we know it's equal to 1. Therefore, the whole thing is 2x plus 2 divided by y squared, right? Because these two things equal to 1. Okay. Everyone's on board. So this is what's written here. So let's continue this fun exercise. Next we compute this one here. Yes. So it's this divided by this. So it's this divided by this. So we have this one is 2x squared plus 2x divided by y squared, 2x plus 2 divided by y squared. So the y square simplify. So we get, well, we get 2x times x plus 1 divided by 2x plus 1. So this is equal to x. So that whole thing is equal to x. That's what's written here. This is equal to x. And then for the next one, maybe I can just tell you. So the next one, if we take this one here and we multiply it out, or maybe I can just do it fast. So we have 2x plus 1 divided by y. The bottom one here we saw is just 2x plus 2 divided by y squared. So 2x plus 2 divided by y squared. So we get, so the 2 cancel, we have x plus 1 divided by y, and then here we have x plus 1 divided by y squared. So this is just equal to y. So that's the calculation we see here at the bottom. And hopefully Nunsongi agrees. Okay, so that's that. And so so summary, we can transform the equations of line and circle into each other. So conclusion, line and circle are essentially the same. Yeah. Okay. So now now with that knowledge, let's try some other examples. Okay. So the next example is this one. So we have a t here, and here we have, x, y, such that y squared equals x cubed. Fortunately, I have a lot of dreams, and my dream today was to do it this way. This is a legal move, because if we take we have to check this equation, right? So y squared is this one squared, is indeed equal to x to the cube, which is this one cubed. Then the map the other way around is xy goes to y divided by x. And then we can just check that, if t goes to t squared, t cubed, and then goes to y divided by x, we indeed get back t. Then if xy goes to y divided by x and then goes to t squared, so this is y squared, x squared, and the next one is y cubed, x cubed, then this is, well, we know that we have this equation here. So this is x cubed divided by x squared. And we know we have this equation here. So this is y cubed divided by y squared. So this is indeed x comma y. So they are essentially the same. Yeah. So I noticed what happened is, before we had the equation of degree 2. So this was before it was degree 2. And now we're looking at something of degree 3. Yeah. And of course, now we think that it's always going to work out. So let's check if it's always going to work out. Here's our next example. We have y squared equals x cubed plus x squared. Yeah. So here again we have t. So this is xy, such that y squared equals t cubed plus x squared. Again, my dreams are very good about this. They told me that t should go to t squared minus 1, t squared minus 1. This is a legal move, because if we compute x to the cubed, so x is this one, we take it to the cubed. Plus to the squared, then we get t squared plus 1 squared, and then t squared minus 1 plus 1, right? So I factor this, and this is indeed equals to t squared plus 1, everything to the squared, which is indeed this expression here. Yeah. And then you can check, you can check that magic trick works. So you can just compute it. Maybe I won't do it here. Okay, now it seems like it's always going to work, right? And we look at the next example, which are smooth cubics, which is this equation here. So until now, we were always looking at, we had a line which was parameterized by t, right? We had a line here, parameterized by t. Then we had some equation which was x, y, in this case, y squared equals x cubed minus 3x minus 3. And then we tried some magic trick and it worked out. Can we do the same here? Can we do the magic trick? So now if we had time, I would tell you go home and try to do it. And then 1 week later, you would tell me you couldn't do it. So I say try again. Then 1 month later, you come back and you say you still couldn't do it. I tell you try again. And then 1 year later, you come back and I ask you, could you do it? You said I still couldn't do it. And then you just keep trying, and you never succeed because it's actually hopeless. So that's not a nice exercise to do. And here's the image, because these poor souls here, they're trying to do the magic trick. You know, they're trying magic trick, but it's hopeless. And 숙명여대 수학과 마스코트 눈송이, she knows that it's not possible. So that's why she tells us just do the math. It's not possible. Yeah. And basically what this means is because the magic trick does not work, they're not rational, but instead they're irrational. So this is what I mean by irrationality in algebraic geometry. This is shapes that are not rational. And trying to understand this is one of the hardest questions. Trying to understand which shapes are not rational is really, really hard. And I'll say something about this for the remainder of the talk. So rationality. So I said deciding when is a space rational or not is extremely difficult. So to show that something is rational, we need to do a magic trick. So that's what I was saying earlier is maybe you try a magic trick for 10 years. And you know, maybe after 10 years, you could never do the magic trick. But that doesn't mean that it's not rational. It just means you couldn't do it, right? So then maybe after 10 years, after trying 10 million times and nothing working, you need to think about it. Well, is there another way to show maybe it's not rational? You know, you tried 1 million times, it didn't work. So maybe it actually doesn't work. And in order to show that something is irrational, to show that the magic trick doesn't work, what we do is we associate some invariance to it. This is how it works. So we have, we have n space, and then we associate some structure. I'm going to call it alpha. And then we have alpha of n space. And usually, because that's always, because n space is the simplest object, that structure is always 0. Yeah. And then we look at the shape that we're interested in, and we associate the structure to it. And if we find that the structure is non-zero, then we can say that, well, we can say that shape is irrational. So if this is true, yeah. So in this study, we have to find structures. We have to have good ideas for good structures. Then we have to show that for n space, the structure is 0. That's usually easy. And then we have to show that for the shape we're interested in, it's non-zero. And that's the really hard part. Because what happens is we try so hard to find new structures. And then either we find that the structure is 0 for the shapes we're interested in, so we cannot argue like this, or it's so hard to compute for the shape that we don't know what the answer is. So it's really mind-boggling. It's very, very, very difficult. And there's really something very, very interesting happening there. It's so hard to find shape, structures that work. And when we find a structure that works, it's too hard to calculate. So that's one thing that people study a lot about rationality. So let's go back to our example here. So that's this example, right? The Noon Songi's favorite example. And so we have, right, so these guys are trying the magic trick. It doesn't work. And now I told you the way to do it is find a structure, compute a structure for the line, compute a structure for the shape, show they're different, and then we can show it's irrational. Yeah. So let's try to do it here. So we need to change our paradigm. So you know, oftentimes when you're trying to solve a math problem, you have to look at it from a different angle. And what we have to do is look at it over the complex numbers. So I'm going to assume that everyone knows what the complex numbers are. If you don't, instead of just the real numbers, we just add I, and I is the square root. I is square root of -1. Yeah. So we decide that it's really not nice that we don't have a square root of -1, so we just add it. But probably you all know that. So instead of looking at this, so before we were looking at this equation over the real numbers, so before, or the rational numbers if you prefer, if you don't like real numbers. And now we're going to look at it over C. Yeah. And then what happens is actually the the shape, if we look at it over C, it looks like this. Yeah. And if we look at the line, and if we look at it over C, so this is over C, well, it looks like this. So this is the over C. So this is the sphere. And this is the, you know, outside of the donut. Okay. So now we changed, we changed the way we looked at the problem, and looking at over C, we get this very different shapes, right? This is very different from what we had here. Somehow this is a cross section. Now, what is this structure? What could it be? Well, if we look at them, like, how can we distinguish them? What is the essential property that distinguishes them? What is the essential property that distinguishes them? Well, alpha is number of holes. Yeah. So if you look at this one, there's one hole. So there's this hole here. And so one hole. And here there's 0 hole. Yeah. So alpha of this one, the number of holes is 0. Alpha of the other one, the number of holes is 1. And as we all know, 1 usually, or maybe always, is not equal to 0. And this means that this one is not rational. All right. So we exactly applied this idea that, well, first we tried to find a magic trick for 5 years. After 5 years, we decided, okay, it's time to try to find a structure that distinguishes them. We have this change of paradigm where we look at it over the complex numbers. Then they become these nice geometric shapes. We see that the essential property of them is the number of holes. We compute the number of holes on both sides. It's a different number, so the structure is different. In conclusion, the shape is not rational. The shape is not rational. Great, wonderful. And now you might think that, well, actually, it's not that hard, right? It's not so difficult. But in fact, it's extremely difficult. Because now, if we want to look at something more complicated, for instance, this shape here, which we saw earlier. So this shape is actually still possible. So this is, this is degree 3 and surface. So before this was a degree 3 curve. Right? Because we have a 3 here. So the highest degree is 3, and we found this nice structure, which is the number of holes. Now we're looking at the degree 3 surface. This is what it looks like. And in fact, you can show that there's a magic trick where if you remove 6 lines, so this surface here has a number of lines, and the number of lines is now I don't remember. So I think it's 15 lines. It has 27 over the complex numbers, but over the real numbers, I think it has 15. If you remove 6 of them, so you just choose 6 that you want to just remove, and they shouldn't like have triple intersections. And then that's exactly the same as the plane where you remove 6 points. It's kind of an incredible fact, yeah? So if you look at this, you never think that if you remove 6 lines, then it's the same as this one. But it's actually it is actually the case. So that's the magic trick. And then we conclude that cubic surfaces are rational. Yeah. So remember, in the beginning, we did degree 2 curves. Do I have a, yeah, we did here. So we did degree, so summary so far. So we started with degree 2 curves. So this was circle. So this is rational. I mean, A is rational. And in fact, all degree 2 n shapes are rational. So that's kind of easy to that's easy to show. So this is easy. Then 2, we did degree 3 curves are irrational. That's kind of semi-hard. Then we did degree 3 surfaces are rational. That's also kind of semi-hard. May take some theory. And then the next example is, of course, degree 3. So the next example is degree 3 threefold. So spaces of dimension 3 that are given by degree 3 equation. So for instance, this is the Fermat cubic. because the equation is like a Fermat equation. And so this is a degree 3 equation in 4 space. This is irrational. That's a very celebrated theorem. It's very complicated, very hard. Celebrated theorem. And now I can already tell you the most famous, one of the most famous conjectures in algebraic geometry is that if you try to do this for dimension 4 or higher, it should also be rational, but we have no idea how. So if we take kind of the same equation, but now we look at it in, so we look at it in dimension n plus 1. So this is dimension n. So it's a cubic, cubic n-fold. Then the conjecture states that this thing is irrational. And so, you know, going back, what we were trying to do, so, you know, to try to show it's rational, we would try magic tricks. But, you know, we've tried magic tricks for more than 100 years, maybe 150 years. We never found magic tricks for this. So maybe magic tricks don't work. So that means we need, you know, we need a structure. We need a structure. And always, so in the structure alpha, such that if this is x, let's call this xn, such that alpha of xn is non-zero. So usually, you know, alpha of n space, n space will be 0. So we need to find a structure such that alpha of xn is non-zero. And so always either two things happen. Alpha xn is 0. So people try very, very hard to find structures, or alpha xn cannot be computed. So for 100 years or maybe 150 years, we always try to do this. So first we tried magic tricks, it never works. Then we try to find these structures, and either the structure is 0, in which case it doesn't help, or the structure is so complicated we cannot compute it. And you know, why do we care? Well, this is a really fundamental question in algebraic geometry, is to be able to determine when is a shape essentially the same as n space. And this very simple question has been one of the driving forces in algebraic geometry. And you know, sometimes you have these guiding problems, and if we can understand when are two different shapes the same, that will help us to understand what algebraic geometry is about. All right, so I had some applications to cryptography. I'm just going to skip it. So this is, you know, I'm just say a couple words. So this is RSA algorithm, and use it, you know, you want to make a more general RSA algorithm using multiplicative structures. This one has a multiplicative structure, and you do it over finite fields. And then using magic tricks, you can actually do this, because when you introduce this over some finite fields, you have a problem that you have to store it in too high of a dimension, and that's inefficient. You know, your computer is gonna, like, your memory is gonna be too small. So instead, what you do is you use a magic trick to compress the information, and using this you can make more general algorithms. But anyways, let me just finish for today, since we're already out of time. So in the beginning, I asked you, what is mathematics to you? And, you know, it's a lifelong endeavor to try to understand what is mathematics. I hope I could give you a little bit of an idea what it means to be thinking about mathematics, what it means to try to understand algebraic shapes. And, you know, one of the things mathematics is about is it's about understanding. So this is an image that occurs in a paper with Trek Kyosunim, and you know, it's kind of this like simple image really explains what our paper is about. So it's really about understanding and reduce to the simplest possible example. So we worked on this for a very long time, and in the end, you know, this explains everything in some sense. And then also mathematics is an exploration, and it's a fascinating exploration. It's a fascinating journey. And this picture was taken in Switzerland, where I'm from, doing a hike. All right, so thank you very much for your attention. It's really a pleasure to be able to talk to you. And that's the end of my talk.
Thank you for the nice talk.
Thank you very much.
So,
감사합니다.
any question from the audience?
Yes, I have one. Hello.
Hello.
It was a
Israel has a
great,
question. Okay.
yeah, it was great lecture, and I think you have a great sense of humor because you read your dream mathematically. I have one question. Why do you call it rational?
Oh, that's an excellent question. You know what? I think I don't know the answer. That's such a good question.
So because I think it's because the magic trick is given by rational functions.
Ah, that makes sense. Yeah. So there's an expression in mathematics which is called rational functions, which is these ratios. If you remember, our magic tricks were something like this, right? And then and those are rational functions. That's thank you. I learned something new.
Good.
So these are very good, very good. Thank you for your question. Such a good question, and thank you for answering it.
자, 레이셔널이란 말이 유리함수라는 뜻이에요. 레이셔널 그 이성적이라는 뜻이 아니라 여기서는 유리함수, 그러니까 그 폴리노미얼, 두 폴리노미얼의 레이셔로 주어지는 레이셔널이 레이셔에서 온 말이에요. 유리함수, 그리고 우리말로는 레이셔널 유리다항체라고 부릅니다. 네. Okay, I said few words in Korean. Yeah.
Thank you.
Any other questions? Any other questions?
I see that 숙명여대 수학과 마스코트 눈송이 is part of is also taking part of the talk. Maybe she has some questions.
I also have a question. So other than the magic trick, are there like any other better discoveries about how to like know if it's rational or not?
That's an excellent question. That's really excellent question. And you know, it's kind of ridiculous because we don't have better tricks. It's mind-boggling, right? It's like such a simple question, like, and we don't have better tricks. All we can do is we can kind of try to formalize the magic tricks. You know, we can say like we can make them kind of less, you know, by hand, make it like a little bit more formal, but we don't have better ones. Like one example would be, you know, we can say something like stereographic projection, where, you know, you have a line, and so you have somehow we have a degree. Okay, maybe I should at least try to write a bit nicer. So we can say that, well, we have a line, we have a degree 2 hypersurface, and then we can do stereographic projection, which is that we have a line that goes like this, and then it meets the hypersurface. So this is a degree 1 hypersurface. surface in one point. And then we can say that the magic trick is exchanging these 2 points. So we can kind of formalize it a little bit, but we don't have a better tool. It's incredible, right? It's like such a basic question, and we don't know how to do it in any better way. Excellent question. Thank you for asking.
So I think the question is whether we can determine if some shape is rational or not without explicitly finding the equations. So if the question is like that, we do have some method, right? So for example, for the algebraic curves, we can find the genus.
Yes.
To determine if it is rational or not. So there are algebraic way to do that.
That's correct.
Yeah.
It is though only in a relatively restricted setting, right? So what you're saying is that in low dimension this is possible. And yes, but I think in higher dimensions we don't.
Yeah,
really
in higher
know.
dimension it is very difficult. Yeah.
But you're right in yeah. Thank you for saying this. Yeah, in low dimensions we have absolutely, yeah. Thank you.
Yeah, because it seemed like the magic trick is applicable to like simple equations, like the first one that we solved. But then, as you mentioned, like the other sophisticated equations seemed like it was like very complicated.
Yeah, very true. If you try to do this with more complicated equations, then it's very quickly a big mess. Yeah. Does all of that make sense? Is that yeah.
Yes, thank you.
Oh, thank you very much for asking.
Okay, thank you. So any more questions?
Thank you for your good talk. I really enjoyed it. And
I'm glad to hear it.
I believe the number of holes is topological invariant.
Mm-hmm.
So is today's topic also applicable to topology?
If it's applicable to?
Topology.
Ah, yeah.
Topology.
Yeah, yes. So sorry. I wasn't sure if you said topos or top. Yeah. Anyways, that's another very good question. And what happens here is really, thanks for asking, excellent question. What happens here is we have a mix between topology and algebraic geometry, because oftentimes mathematics is not like strictly distinguished between different topics, but there's like always a back and forth interaction. And when I set number of holes, that's exactly a topological concept. Now you can ask the question, how do you define number of holes in an algebraic way? How do you define this just from the equations? And maybe you want to do this because you don't, if you're working over the real numbers or the rational numbers or finite fields, maybe you don't want to look over the complex numbers. So basically, yes, there's a very strong interaction between topology and algebraic geometry. And oftentimes we get intuition from topology and translate it into a concept in algebraic geometry. In particular, the number of holes can be defined in a purely algebraic way. So yeah, really big interaction there between algebraic geometry, topology, also number theory, and many other things. Does that answer your question more or less?
Thank you. And I'm interested in this topic to study further. So is there anything you recommend to study as an introduction for this?
Oh, that's a really good question. So one time Professor Tre recommended to me a book, which I think is very good, which is a problem-solving approach to, is that correct? A problem-solving approach. I think that's really, is that a really good book as an introduction?
Yeah, I think so, yeah.
Yeah, so I think that's a really excellent one. Problem-solving approach to, I think, algebraic geometry.
The other way, so algebraic geometry, problem-solving approach.
Okay, very good. So fortunately, I have a tablet, so I can just do this. Well, okay, didn't work so well. doesn't always work. So it's like this. and
I
then-
show what it is.
Okay. So, okay, well, a problem-solving approach. Yes. Yeah. So maybe that's a, yeah, I think that might be a good place. I think it's also a fun book because you can play around and work with it, etc.
Yes. Thank
Yeah,
you very
thanks for
much.
asking. Well, thank you for asking. Good question.
Okay, thank you for the talk and all the questions. Any more questions? I guess your talk was very nice and clear. So
Well, I'm really happy to hear that. It's you know, it's a pleasure to be able to give this talk and you know, to at least virtually visit visit you this year. And
sure, I'm
yeah,
looking forward to it.
I'm looking forward to visiting as well. Yeah.
Okay.
Are you back to in-person teaching, or is it everything still online?
Online?
Everything online, yeah.
Yeah.
What about next semester?
We don't know.
I don't know. Yeah. In the UK, they pretend like there's nothing happening, so everything is in person.
They don't wear mask at all.
They don't wear that. It's like really incredible. Yeah, really incredible.
Anyway, so if there is no more questions, then we thank our speaker Michel Garrel again. And 이상으로 콜로키움을 마치겠습니다. 네, 수고하셨습니다.
Yeah, thank you very much for the invitation. It's
Yeah,
a pleasure
thank
to
you.
be here. Thank you.
Yeah. Bye bye.
Bye bye.
Nice.